James Webb saw something 13 billion years away that shouldn't exist. The observable universe has existed for approximately 13.8 billion years, and the standard model of hierarchical structure formation allocates the first 500 million years of that span to the production of faint, low-mass stellar seeds rather than fully assembled galactic systems. That allocation is not a stylistic preference among cosmologists, but a derived consequence of three inputs treated as fixed: the gravitational constant, governing the rate at which matter aggregates, the thermodynamic behavior of primordial gas as it cools and fragments, and the finite interval between the initial singularity and any given observational epoch. Any measurement returning stellar assemblies that exceed the mass, luminosity, or organizational complexity permitted within that interval implicates one of the three inputs, and the identification of which input has been misjudged constitutes the central analytical problem of contemporary early universe cosmology. The framework within which galaxies are understood to assemble carries the name hierarchical structure formation, and its central claim is that gravitational aggregation proceeds from small scales to large scales rather than in the reverse direction. The smallest dark matter over densities collapsed first, drawing in surrounding material through gravitational attraction, and these low-mass halos subsequently merged with one another to produce progressively larger gravitational wells. The largest structures observed at the present epoch, including galaxy clusters and superclusters, are understood as the accumulated end product of billions of years of successive mergers rather than as objects that condensed at their present mass in a single event. The timetable governing this bottom-up assembly is not arbitrary. It is fixed by the growth rate of gravitational instabilities operating on the density perturbations imprinted during the inflationary epoch, and that growth rate is itself set by the mean density of matter and the expansion history of the universe. Within this framework, the dark matter halo functions as the indispensable scaffold on which any luminous galaxy is constructed. Ordinary baryonic matter, consisting principally of hydrogen and helium in the early universe, cannot collapse into stellar systems on its own within the available cosmic time because radiation pressure and thermal motion resist gravitational contraction below a certain mass threshold. Dark matter, being non-interacting with electromagnetic radiation, is subject to no such pressure support and collapses freely into gravitationally bound halos as soon as the ambient density permits. Only after these halos are in place can neutral gas fall inward along their gravitational potential wells, and the sequencing is not reversible. The scaffold must exist before the visible structure can be raised upon it. The consequence is that the maximum stellar mass any galaxy can contain at a given epoch is bounded above by the maximum halo mass available at that epoch, which is itself dictated by the halo mass function derived from the standard cosmological parameters. Once neutral hydrogen and helium fall into a dark matter halo, the gas must radiate away its gravitational potential energy in order to condense further, and the efficiency of that radiative cooling depends on temperature, density, and chemical composition. Primordial gas, containing essentially no metals beyond trace lithium, cools inefficiently at temperatures below approximately 10,000 Kelvin because the principal coolants available to enriched gas, carbon, oxygen, and their ionized transitions, are absent. The earliest stellar generations, designated Population 3, are therefore predicted to have formed from molecular hydrogen cooling in mini-halos of roughly 1 million solar masses, producing individual stars of unusually high mass because fragmentation was suppressed by the elevated cooling temperature. These first stars completed their life cycles within a few million years, seeded their surroundings with the first heavy elements through supernova ejection, and thereby enabled the subsequent formation of Population 2 stars at more conventional masses within halos that had accumulated the necessary metallicity. The rate at which infalling gas is converted into stars, designated the star formation efficiency, is not a free parameter within the standard model. It is calibrated against observations of galaxies across a wide range of masses and redshifts, and the calibrated value implies that only a small fraction of the baryonic mass entering any given halo is converted into stellar mass within a dynamical timescale, typically on the order of a few percent to 20%, depending on halo mass and environmental conditions. Radiative feedback from young, massive stars, supernova-driven galactic winds, and the ionizing background produced by early star formation all act to suppress further collapse by heating and expelling the residual gas reservoir, and these feedback processes impose a ceiling on how rapidly any single halo can accumulate stellar mass, regardless of how much gas is nominally available for consumption. Combining the halo mass function at high redshift with the calibrated star formation efficiency yields a specific prediction for the stellar mass content of galaxies observable in the first several hundred million years after the initial singularity. At redshift 7, corresponding to an age of approximately 750 million years, the standard framework permits typical stellar masses in the range of 100 million to 1 billion solar masses per halo, distributed according to a halo mass function that falls steeply toward the high mass end. At redshift 10, corresponding to an age of approximately 470 million years, the permitted range contracts further because both the halo mass function and the integrated star formation history have had proportionally less time to develop. Stellar masses on the order of 10 billion solar masses at redshift 10 are not merely improbable within the standard framework. They are excluded because neither the required halos nor the required duration of prior star formation is available at that epoch. The identification of any galaxy with a specific epoch depends upon the measurement of its redshift, and the physical basis of that measurement rests on the cumulative stretching of electromagnetic radiation as it traverses the expanding metric of space. Emission produced in the rest frame of a distant galaxy is systematically shifted toward longer wavelengths by the time it reaches an observer, and the fractional shift is directly related to the ratio of the scale factor of the universe at emission and at reception. A galaxy whose light is observed with a redshift of 10 emitted that light when the universe was approximately 1/11th of its present linear scale, and the interval between emission and reception is calculable from the assumed expansion history to within a precision limited principally by uncertainty in the cosmological parameters themselves. Redshift is therefore not an approximate proxy for age, but a direct kinematic and geometric quantity from which age is derived through the field equations governing cosmic expansion. Two techniques dominate the assignment of redshifts to faint, high redshift candidates: photometric estimation and spectroscopic confirmation. Photometric redshifts are inferred by measuring the flux of a source across a series of broad wavelength bands and identifying the position of the Lyman break, the sharp discontinuity produced when neutral hydrogen in and around the source absorbs all radiation blueward of 121.6 nanometers in the rest frame. The wavelength at which this discontinuity appears in the observed spectrum fixes the redshift to within a range of typical uncertainty of a few tenths, sufficient for statistical population studies, but not for individual object confirmation. Spectroscopic redshifts, obtained by resolving specific emission or absorption lines within the source spectrum, provide precision at the level of the 4th or 5th decimal place and are the only measurements considered definitive for individual high redshift candidates. The distinction matters operationally because photometric estimates are known to produce a small but non-negligible fraction of catastrophic misidentifications, in which a low redshift dusty galaxy is mistakenly assigned to the early universe on the basis of an incorrectly located spectral break. The instrument constructed to test the assembly bounds derived in the preceding analysis operates from the second Sun-Earth Lagrange point, a gravitationally stable position approximately 1.5 million kilometers from Earth along the anti-solar axis, where the combined gravitational fields of the Sun and Earth permit a spacecraft to maintain a fixed relative position with only minimal propellant expenditure for station keeping. The choice of this location is not incidental to the science, but is dictated by the thermal requirements of infrared observation, because any detector attempting to resolve emission at wavelengths between 1 and 28 microns must be shielded from the thermal radiation of any warm body within its field of view, including Earth itself, whose emitted infrared flux would otherwise saturate the instrument and render faint high redshift sources undetectable against the background. The primary mirror of the James Webb Space Telescope consists of 18 hexagonal beryllium segments coated with a thin layer of vapor-deposited gold, arranged in a hexagonal tiling that produces an effective aperture of approximately 6.5 meters in diameter. The segmented configuration was imposed by the launch constraint that the deployed mirror must exceed the diameter of any available fairing, requiring the mirror to be folded during transit and unfolded and phased to sub-wavelength precision after arrival at the operational orbit. The total collecting area of the assembled mirror measures approximately 25 square meters, providing roughly 6.25 times the light-gathering capacity of the Hubble Space Telescope and enabling the detection of point sources at apparent magnitudes approaching 31 in the near-infrared bands with integration times of several hours. The selection of gold as the reflective coating is dictated by its reflectivity profile across the infrared spectrum, which exceeds 98% for wavelengths longer than approximately 700 nanometers and remains essentially flat across the full operational range of the instrument. The coating thickness measures approximately 100 nanometers, applied over a chromium adhesion layer of a few nanometers, and the total mass of gold deposited across all 18 segments amounts to less than 50 grams. The beryllium substrate itself was selected for its combination of low thermal expansion coefficient, high stiffness to mass ratio, and dimensional stability across the wide temperature range between ambient assembly conditions and the cryogenic operational environment, which permits the mirror to retain its polished figure to within tolerances measured in nanometers after cooling by more than 200 Kelvin during commissioning. The thermal control architecture that permits detector operation at the required sensitivity consists principally of a 5-layer sunshield fabricated from Kapton polyimide film coated with vapor-deposited aluminium on both sides and silicon on the sun-facing surface of the outermost layer. Each layer measures approximately 25 meters by 12 meters in its deployed configuration, and the layers are separated by evacuated gaps that permit radiative cooling between successive surfaces. The sun-facing side of the outermost membrane reaches equilibrium temperatures near 380 Kelvin during nominal operations, while the innermost layer facing the instrument module remains below 50 Kelvin, producing a temperature differential across the shield stack of more than 300 Kelvin over a physical thickness of only a few centimeters. The passive cooling achieved through this configuration is sufficient to bring the near-infrared instruments to operational temperatures below 40 Kelvin without any active refrigeration. The mid-infrared instrument, designated MIRI, cannot achieve its operational temperature through passive cooling alone because its detectors, based on arsenic-doped silicon photoconductors, require temperatures below 7 Kelvin to suppress thermal dark current to levels compatible with the detection of faint astronomical sources. A dedicated closed-cycle helium cryocooler operating on a pulse tube and Joule-Thomson expansion cycle brings the MIRI focal plane to approximately 6.7 Kelvin, extracting the residual heat that passive radiation cannot remove and dissipating it into the cold side of the sunshield through a network of thermal straps. The cryocooler represents the only significant active thermal management subsystem on the observatory, and its continued operation is a limiting factor on the total mission duration alongside the propellant reserve available for station-keeping maneuvers. The near-infrared imaging capability is provided by the NIRCam instrument, which incorporates 2 identical optical modules operating in parallel across adjacent fields of view, each equipped with mercury-cadmium telluride detectors sensitive to wavelengths between approximately 600 nanometers and 5 microns. The instrument provides simultaneous imaging in a short wavelength channel covering 600 nanometers to 2.3 microns and a long wavelength channel covering 2.4 microns to 5 microns, with a dichroic beam splitter directing the appropriate portion of the incident spectrum to each detector array. The pixel scale in the short wavelength channel measures approximately 31 milliarcseconds per pixel, providing angular resolution sufficient to distinguish morphological features in resolved galaxies at redshifts up to approximately 3, while the long wavelength channel operates at 63 milliarcseconds per pixel, matching the diffraction limit of the primary mirror at those wavelengths. The complementary spectroscopic capability required for the definitive confirmation of high redshift candidates is provided by the NIRSpec instrument, which incorporates a microshutter array consisting of approximately 250,000 individually addressable mechanical shutters arranged in a grid pattern across the instrument focal plane. Each shutter measures approximately 100 by 200 microns and can be independently opened or closed to admit or block the light from a specific location in the sky, permitting the simultaneous acquisition of spectra from up to 200 targets within a single field of view. The dispersion elements available within the instrument include prisms and gratings covering resolving powers between approximately 100 and 2700, sufficient to resolve the emission lines characteristic of ionized hydrogen, oxygen, and other diagnostic species in the rest frame ultraviolet and optical bands of high redshift galaxies. The selection of the near-infrared operational band is directly dictated by the physics of cosmological redshift acting on the rest frame emission of early galaxies. A galaxy at redshift 10 emits the majority of its stellar luminosity at rest frame ultraviolet and optical wavelengths, but the cumulative stretching of that radiation during transit shifts the emission into the observer frame near-infrared band between approximately 1 and 5 microns. Any instrument attempting to detect such galaxies through optical observation is blind to their principal emission by construction, because the atmosphere is opaque across most of the relevant wavelength range and because ground-based optical detectors are not sensitive to the shifted band. The infrared operational domain is therefore not a design preference among several equivalent options, but the only wavelength regime in which high redshift galactic emission is accessible from a space-based platform. The Lyman break identification technique, which underpins the selection of high redshift candidates from the initial imaging data, relies on the systematic absorption of radiation blueward of the Lyman alpha transition by neutral hydrogen distributed along the line of sight between the source and the observer. Emission at rest frame wavelengths shorter than 121.6 nanometers is absorbed by intervening neutral hydrogen with high efficiency, producing a sharp discontinuity in the observed spectrum at the wavelength corresponding to the redshifted Lyman alpha transition. The identification of this discontinuity across successive photometric bands permits the assignment of a redshift range to any source detected in the imaging catalog, with the precision of the assignment limited principally by the width of the photometric bands and the signal-to-noise ratio of the individual detections. The observational programs designed to exploit these capabilities in the domain of early galaxy assembly include several coordinated survey campaigns, of which the most significant for the analysis to follow are CEERS, the Cosmic Evolution Early Release Science Survey, and Cosmos Webb. CEERS conducted deep imaging and spectroscopy across a targeted region within the extended Groth strip, integrating the NIRCam and NIRSpec instruments to produce a catalog of high redshift candidates within the first months of operational science observations. Cosmos Webb, executed subsequently across a substantially larger area of approximately 0.6 square degrees, prioritized statistical sampling of the high redshift galaxy population over the depth achievable in more concentrated fields, producing a catalog of several 100,000 sources with photometric coverage sufficient for Lyman break identification across the redshift range from approximately 6 to 14. The measurements returned within the first months of scientific operations included, buried within the CEERS photometric catalog, a single unresolved red source whose spectral energy distribution across the near-infrared bands fitted a redshift of approximately 7.5 and a stellar mass on the order of 100 billion solar masses. The initial identification of this source is credited to Ivo Labbé and his collaborators, whose photometric analysis returned distance and mass parameters that, when combined, described an object incompatible with the assembly bounds derived from the standard framework. A galaxy containing stellar material comparable in quantity to the present-day Milky Way, situated at a cosmic epoch corresponding to approximately 700 million years after the initial singularity, requires either a halo mass far exceeding the maximum permitted by the halo mass function at that redshift, or a star formation efficiency approaching unity across the entire preceding history of that halo. Neither condition is consistent with the calibrated inputs of the standard model, and the discrepancy in the case of the initial source measured approximately 2 orders of magnitude in stellar mass relative to the predicted maximum. The identification of a single anomalous source is insufficient to constitute a structural challenge to any framework because photometric measurements are subject to a range of systematic effects that can produce spurious high-mass, high-redshift detections. Labbé and his collaborators, aware of this limitation, extended their analysis across the remainder of the CARES deep field, applying identical selection criteria to the full catalog of red, compact sources whose spectral energy distributions were consistent with high redshift massive galaxies. The extended search returned 5 additional candidates within the same field, each measuring stellar masses between approximately 10 billion and 100 billion solar masses at photometric redshifts between 7 and 9, and the total population of 6 such objects was subsequently designated the Universe Breakers in the peer-reviewed publication that reported the result in February 2023. The mechanism-level analysis of what the existence of such a population would require proceeds through the 2 independent physical inputs constraining early stellar assembly. The first input is the halo mass function at the relevant redshift, which specifies the number density of dark matter halos of a given mass per unit comoving volume. Within the standard framework, the halo mass function at redshift 8 predicts that halos of mass sufficient to host 100 billion solar masses of stars, assuming baryonic conversion at the calibrated efficiency, should number fewer than 1 per cubic gigaparsec, a density so low that the probability of encountering 6 such objects within the volume surveyed by SEERS is essentially 0. The second input is the star formation efficiency itself, which, if elevated toward unity, would permit smaller halos to host correspondingly larger stellar masses, but the elevation required to reconcile the observed masses with the available halo population exceeds the maximum efficiency ever inferred from any observational calibration by a factor of several. The publication of the initial result produced immediate scrutiny from the wider community, and the systematic corrections examined in the subsequent months proceeded along 3 distinct lines. The first concerned the photometric calibration of the NARCam detectors during the earliest phase of scientific operations, when the instrument response functions were still being refined against in-flight standards and small errors in the flux calibration could produce systematic offsets in inferred stellar mass. The refinement of the calibration during 2023 reduced the inferred masses of several of the original candidates by factors between 2 and 4. Bringing them closer to, but still not within, the standard bounds, and the calibrated numbers stabilized as the instrument entered its mature operational phase. The second line of correction concerned the photometric redshifts themselves. The Lyman break identification technique, while reliable for the majority of high redshift candidates, produces a small fraction of catastrophic misidentifications in which a low redshift dusty galaxy with heavy internal extinction produces a spectral break at a wavelength that mimics the Lyman discontinuity of a genuine high redshift source. Spectroscopic follow-up of the original 6 candidates, conducted principally through NIRSPEC observations across 2023 and 2024, revealed that at least one of the sources sat at a substantially lower redshift than the photometric analysis had assigned, placing it in an epoch during which its inferred mass was no longer anomalous. The revised sample of confirmed high redshift massive galaxies was correspondingly smaller than the original photometric catalog, though it did not fall to 0. The third and most consequential line of correction concerned the interpretation of the compact red morphology characteristic of the anomalous sources. A population of similarly compact and similarly red objects, subsequently designated the little red dots, was identified across multiple JWST survey fields and initially assumed to consist of stellar-dominated galaxies whose luminosity traced their stellar mass through the standard mass-to-light relations calibrated on lower redshift populations. Spectroscopic follow-up revealed that a substantial fraction of these objects exhibited emission line profiles characteristic of active galactic nuclei, specifically the broadened permitted line emission produced by ionized gas orbiting a supermassive black hole within its gravitational sphere of influence. The identification of an active galactic nucleus contribution to the observed luminosity implies that the inferred stellar mass, calculated on the assumption of purely stellar emission, is systematically overestimated by whatever fraction of the observed flux originates in the accretion process rather than in the stellar population. The reinterpretation of the little red dot population as active galactic nuclei rather than stellar systems does not resolve the anomaly in full, because it substitutes one problem for another. If a substantial fraction of the anomalous sources are powered by supermassive black holes of the mass required to produce the observed luminosity, then the assembly of black holes exceeding 1 million solar masses within the first 700 million years of cosmic history is itself a challenge to the standard framework, which allocates comparable timescales to black hole growth through Eddington-limited accretion from stellar mass seeds. The transfer of the anomaly from stellar assembly to black hole assembly reduces the tension in one direction, while introducing it in another, and the current consensus on which fraction of the little red dot population is stellar-dominated, black hole-dominated, or genuinely composite remains contested in the spectroscopic follow-up literature. After the application of all three corrections, a residual population of confirmed massive galaxies at redshifts above 7 remains in the catalog. The residual is smaller than the original 6 candidates, likely amounting to a few objects across the surveyed volume, but it is not zero and it is not statistically dismissible. The discrepancy factor between observed and predicted stellar mass density at redshifts above 7 reaches values of approximately 10 to 30 for the confirmed residual population, reduced from the factor of 100 that characterized the original photometric analysis, but still exceeding the tolerance of the standard framework by margins that cannot be absorbed through incremental adjustment of the calibrated parameters. The residual constitutes a persistent observational challenge whose resolution requires either the identification of a further systematic effect not yet characterized or the modification of the assembly framework itself. A complementary observational channel bearing on the same structural question was opened by the completion of the Cosmos Web mapping campaign and the subsequent analysis of matter distribution on scales exceeding those of individual galactic assemblies. The identification of coherent structures within the mapped volume proceeded through the technique of quasar absorption line spectroscopy, in which the light from background quasars is analyzed for the imprint of intervening gas clouds that absorb specific wavelengths characteristic of magnesium and other diagnostic species. The distribution of absorption systems across the field, when compiled and mapped, revealed geometrical arrangements whose scale and coherence exceeded the bounds predicted by the standard framework for large-scale structure at the epochs surveyed. The giant arc, a curved concentration of absorption systems spanning approximately 3.3 billion light-years across the sky at a redshift of approximately 0.8, and the Big Ring, a near-circular arrangement of absorption systems measuring approximately 1.3 billion light-years in diameter, situated at a comparable redshift and within an adjacent region of the same field. The two structures occupy angular positions separated by approximately 12 degrees on the sky and lie at effectively identical distances from the observer, placing them within the same slice of cosmic time and within a spatial neighborhood whose extent, relative to the observable volume, is small enough that their joint occurrence cannot be attributed to random spatial coincidence without invoking probabilities that the standard statistical framework treats as vanishingly low. The subsequent three-dimensional reconstruction of the Big Ring, performed by resolving the radial distribution of absorption systems along the line of sight in addition to their projected angular positions, established that the apparent circular geometry visible in the two-dimensional projection resolves into a helical or coiled structure whose axis happens to point approximately along the line of sight to the observer. The coincidence of viewing angle required to produce the observed circular projection from an intrinsically helical structure implies either an anthropic selection effect of low probability or the existence of a larger population of similar coiled structures oriented across all directions, of which only those aligned along observational sightlines are readily identified. Neither interpretation is compatible with the standard prediction that matter distribution on scales exceeding approximately 1 billion light-years should be statistically isotropic and structurally featureless. The structural coherence of formations, spanning several billion light-years, imposes an independent constraint on the assembly framework that operates through the finite propagation speed of gravitational influence rather than through the halo mass function. Any coordinated arrangement of matter across a spatial extent exceeding the light travel distance available within the age of the universe cannot have been produced through gravitational interaction operating within the standard causal structure, because the opposite ends of the arrangement have not been in causal contact for a duration sufficient for gravitational forces to have organized their relative positions. The giant arc and the big ring, at their measured spatial extents, approach or exceed the coherence limit derived from the age of the universe and the propagation speed of gravitational disturbances, and their existence therefore constitutes a constraint on the assembly framework operating through a physical input entirely independent of the constraints characterized through the universe breaker analysis. No single modification to the standard cosmological framework currently accounts for both the excess stellar mass identified at high redshift and the excess structural coherence identified at the largest observed scales, and the proposals under active examination in the peer-reviewed literature address these two anomalies through distinct physical mechanisms that resist unification within a single revised model. The situation is characterized not by an absence of candidate explanations, but by an oversupply of them, each partial, each addressing one portion of the observational tension, while introducing or exacerbating tension in another portion, and none yet demonstrating the predictive coverage that would justify its adoption as a replacement for the framework it seeks to modify. The first category of proposed modifications addresses the star formation efficiency parameter directly, positing that the calibrated values derived from lower redshift observations underestimate the efficiency operating in the earliest galactic assemblies. The physical basis for this proposal rests on the low metallicity of primordial gas, which produces stellar populations of systematically higher mean mass than those forming from enriched gas at later epochs, and higher mass stars produce disproportionately larger luminosities per unit stellar mass through their more energetic nuclear burning cycles. A top-heavy initial mass function of this kind reduces the inferred stellar mass required to produce the observed luminosities of the universe breakers, potentially by factors of 3 to 5, and correspondingly relaxes the constraint on the halo mass function required to host them. The proposal is internally consistent within its own domain, but produces a secondary tension with the observed metallicity yields of subsequent galactic populations, because a top-heavy initial mass function operating across the earliest stellar generations would produce heavy element abundances at lower redshifts substantially higher than those actually measured, and the reconciliation of these two constraints within a single physically motivated stellar formation model has not yet been achieved. The second category of proposals addresses the halo mass function itself, positing that the standard prediction underestimates the number density of massive halos at high redshift because the underlying primordial power spectrum contains additional structure on relevant scales that the standard model does not incorporate. A primordial power spectrum enhanced at intermediate scales would produce earlier collapse of larger halos, permitting the assembly of stellar systems of the observed masses within halos that the standard framework predicts should not yet exist. The proposal accounts for the universe breaker population in a physically motivated manner, but requires modifications to the inflationary scenario governing the generation of primordial fluctuations, and any such modification must remain consistent with the temperature fluctuation spectrum of the cosmic microwave background, which has been measured to precisions of parts per 100,000 and which constrains the permissible modifications to the power spectrum within narrow bounds. The third category concerns the properties of dark matter itself, and specifically, the possibility that its collisional or self-interaction properties differ from the collisionless behavior assumed within the standard framework. Self-interacting dark matter models produce halo mass functions and internal halo structures that deviate from the standard predictions in directions that would reduce the tension with the universe breaker observations, but the required interaction cross-sections must simultaneously remain consistent with the observed shapes of galaxy cluster cores, the survival of low-mass satellite galaxies within the Milky Way halo, and the timing constraints on galactic disk formation. The parameter space within which all these constraints are simultaneously satisfied is narrow, and the models occupying it have not yet demonstrated the predictive success across all relevant observations that would justify their adoption over the standard collisionless framework. The proposals addressing the structural coherence anomaly operate through mechanisms distinct from those addressing the mass anomaly and cannot be unified with them through any modification of the star formation or halo assembly parameters. The most physically motivated of these proposals invokes the existence of cosmic strings, one-dimensional topological defects predicted to have formed during phase transitions in the very early universe as different regions of space adopted incompatible vacuum configurations at the boundaries between which the fabric of space was left in a strained topological state. A cosmic string extending across cosmological distances would carry an enormous mass per unit length, on the order of tens of billions of solar masses per light year, and its gravitational field would organize the surrounding matter distribution along its length, potentially producing the coherent large-scale structures observed in the mapping programs. The proposal is theoretically well developed, but rests on the existence of a class of objects that has never been directly detected in any observational program, and the parameter space within which cosmic strings could produce the observed structures without producing additional gravitational lensing signatures already excluded by direct searches is narrow. A more speculative category of proposals invokes cyclic or bouncing cosmological models, in which the observed universe is understood as one phase within a larger sequence of expansion and contraction cycles, and in which structural features imprinted during previous cycles could persist as observable signatures within the present cycle. The best developed of these proposals is the conformal cyclic cosmology framework advanced by Roger Penrose, within which the very late time state of one cycle is identified conformally with the very early time state of the next, permitting large-scale features from the previous cycle to persist as circular or ring-shaped anomalies in the microwave background and in the large-scale distribution of matter. The identification of the Big Ring with such a persistent feature has been suggested but not established, and the proposal remains outside the consensus of active cosmological research pending the identification of confirming signatures in additional observational channels. The status of the little red dot population, whose reinterpretation as active galactic nuclei rather than stellar systems, reduced but did not eliminate the mass tension identified in the initial universe breaker analysis, remains contested within the spectroscopic follow-up literature. Individual sources within the population have been characterized in detail through NIRSPEC observations returning resolved emission line profiles, and the balance of stellar and accretion contributions to the observed luminosity varies substantially across the population. A subset of sources exhibits emission line widths consistent with black hole masses of approximately 10 million to 100 million solar masses at redshifts above 7. A subset exhibits narrow emission characteristic of pure stellar photoionization, and a substantial intermediate subset exhibits composite spectra whose decomposition into stellar and accretion components remains ambiguous. The population as a whole does not admit a uniform classification, and the fraction of the original universe breaker sample that ultimately resolves to genuine stellar-dominated massive galaxies at high redshift will not be established until the spectroscopic follow-up catalog reaches statistical completeness across the relevant mass and redshift ranges. The forthcoming observational programs designed to address these unresolved questions include the continued deep spectroscopic follow-up of high redshift candidates through the J-STWIST Cycle 3 and Cycle 4 programs, the wide-field structural mapping to be produced by the Euclid mission over the next 6 years, and the photometric survey volume to be delivered by the Vera Rubin Observatory across the southern sky. Each of these programs addresses a distinct aspect of the observational challenge. The JWST follow-up will establish the confirmed sample size of massive high redshift galaxies to statistical precision sufficient to distinguish between the proposed modifications of the assembly framework. The Euclid mission will map the three-dimensional distribution of matter across a substantial fraction of the observable. volume with the angular precision required to characterize the frequency and properties of coherent large-scale structures, and the Rubin photometric survey will deliver a catalog of several 100,000 galaxy clusters and supercluster candidates against which the statistical properties of the structural anomalies can be tested for consistency with any modification of the standard framework. The current sample of spectroscopically confirmed massive galaxies at redshifts above 10 stands in the low dozens as of the completion of Cycle 2 follow-up observations. The sample size projected to distinguish between the leading modifications of the assembly framework is estimated at several hundred, an increase by an order of magnitude that will require the sustained execution of dedicated follow-up programs across the remaining nominal lifetime of the JUICE mission. The corresponding sample of confirmed coherent structures at scales exceeding 1 billion light-years currently includes the Giant Arc, the Big Ring, the Sloan Great Wall, the South Pole Wall, and the disputed Hercules Corona Borealis Great Wall, and the extension of this sample through the Euclid and Rubin programs will establish whether these formations constitute rare outliers within a fundamentally isotropic distribution or the visible extremes of a distribution whose statistical properties differ systematically from the standard prediction. The mechanism governing early galactic assembly, as currently modeled through the standard framework of hierarchical structure formation, cannot produce what has been observed within the first billion years of cosmic history. Either the mechanism itself is incomplete, requiring the incorporation of physical processes not yet included within the calibrated framework, the observations are subject to systematic biases, not yet identified, across multiple independent measurement programs simultaneously, or the underlying inputs to the model, the age of the universe, the expansion history, the primordial power spectrum, or the nature of dark matter, differ from their assumed values in ways that current observational precision has not yet resolved. Each of these possibilities carries substantial theoretical and observational consequences, and the data currently available cannot yet distinguish between them. The instrument was constructed to test the framework, and the framework as constructed cannot yet accommodate the test result it has returned. The observational program continues, and the resolution of the discrepancy remains open.